Hello, welcome in the first lecture of my course Convective Heat Transfer. In this course basically we will be discussing about what things we are going to study, okay, and what different terminologies we are going to use throughout this course. Obviously, at the beginning I will tell you that what is the necessary books, okay, for understanding this course. Okay. So, to begin with I have named this lecture as introduction lecture. Okay. So, in this lecture first I will be introducing myself. So, I am actually Dr. Arup Kumar Das. Okay. I am Dr. Arup Kumar Das. I am assistant professor in the Department of Mechanical and Industrial Engineering of Indian Institute of Technology, Roorkee. Okay. So, you can note down my email ID akdasfme faculty mechanical engineering @iitr.ac.in, and you can also note down my telephone number. If you have any query or doubt, you can always post me email or you can contact me via this telephone number. Okay. You can also go through my web pages for better knowing that what type of research work at present I am doing. This is a very nice and interactive web page what I am having, two-phase IITR in weebly.com, okay, as well as you can also visit my IITR official web page. So, this goes like this. Okay. In this course I will be having two teaching assistants. They will be basically communicating with you, Mr. Pramod Kumar, okay, and Mr. Digvijay Singh. So, you may please note down their email IDs, okay, and their telephone numbers, okay, respectively. Okay. So, if you have any query or any doubt, definitely there is a discussion forum for this course, but in certain cases you may also contact them. Okay. So, with this introduction, little brief introduction, let me first tell you that what things we are targeting in the course. So, I will be showing you the syllabus what we will be covering. As you know, this course is for 10 actually hours. So, we have distributed this 10 hours into 20 lectures, okay. More or less all the lectures are having length of 30 minutes, okay, plus minus 30 minutes. So, you see we are having actually 10 hours, that means 4-week course. So, the week I have distributed like this. So, week 1, week 2, week 3 and week 4, and each week I will be giving you 5 modules, okay, module 1 to module 5. So, altogether we will be having 20 modules. Okay. So, as I am doing over here, in the first module we will be discussing about introduction, and then I will be giving you idea of different modes of heat transfer. Okay. Then immediately in the next lecture I will be discussing that how energy can be balanced, as it is convective heat transfer. So, energy is very important. So, I will be showing you how energy balance can be done and what is the governing equation for energy conservation. Okay. Then in the next lecture, that means week 1 module 3, I will be showing you that how energy equation can be written in different form, especially CP form, CV form, all these specific heat forms we will be showing you. Okay. Then in this week only we will be giving you idea of thermal boundary layer. Okay. So, this is nothing but flow over a flat plate if it happens, and the plate if it is having higher temperature compared to or some other temperature compared to free steam temperature, whatever flow is coming, then we will be having a concept of boundary layer development, just like your hydrodynamic boundary layer. This boundary layer we will be calling thermal boundary layer, and this we will be discussing in module 4. In this week, last module we will be keeping for forced convection. Okay. So, we will be having some predominant flow over a flat plate. So, we will be having forced convection, and in this case, in this lecture we will be discussing about extreme limit of low Prandtl number. Okay. Immediately in the next lecture, that means week 2 module 1, we will be discussing about high Prandtl number extent. So, these two will be more or less discussing same phenomenon, but discussing two different extents. Okay. Then we will be going for another analogous case, which is uniform heat flux of the plate. In these two cases we will be actually having constant temperature, but here we will be having uniform heat flux, okay, supplied by the plate. Okay. So, this case we will be seeing over here. Then in second week we will be briefly seeing that what is natural convection, and we will be seeing two different extents of natural convection: uniform wall temperature and uniform heat flux. Okay. At the end of this week we will be doing some tutorials, okay, on convection over a flat plate. Okay. We will be going for some sums, numerical sums, okay, which will be covering all these lectures over here. Okay. Then in week 3 we will be moving towards flow inside a channel. Okay. So, internal flow situation. So, a previous things was flow on a flat plate, external flow. Here we will be seeing forced convection inside a duct, internal flow. Okay. Then in that week only we will be continuing thermally developed slug flow. So, we will be discussing what is slug flow and what is thermal development. Okay. So, thermally developed slug flow we will be seeing, okay, in second module of third week. In third module we will be seeing thermally and hydrodynamically both developed flow, okay, but we will be considering first uniform heat flux case in module 3, and in module 4 we will be seeing uniform wall temperature case. Okay. So, at the end of this week, that means week 3, in module 5 we will be seeing another extent which is called thermal entrance region. So, this is actually the beginning section of the duct, okay, for convective heat transfer. So, we will be defining what is entrance region, and then we will be knowing that what will be the governing equations and different non-dimensional numbers for uniform wall temperature case. Okay. Last week at the beginning we will be continuing and we will be seeing the same case, thermal entrance region for uniform heat flux case. Okay. In this week, in the second module, we will be seeing a special type of convection called Rayleigh-Bénard convection. In this, we will be seeing that whenever we are having two parallel plate, in between that how convection cells form, and then how that can be seen using governing equation, okay, and boundary conditions respectively. And then we will be seeing two special cases related to convection only. First one is heat transfer with phase change. So, I will be showing you how phase change can be linked up with convection. Phase change means it will be only boiling and condensation. In other cases convection will not be that much involved. Okay. So, we will be seeing boiling and condensation cases over here, and then we will be seeing the mass transfer, which is more or less analogous to your convective heat transfer, and this lecture will be very much related to your chemical engineering students. Okay. And then at the end of this lecture we will be doing once again some tutorials, and in this tutorial we will be specially concentrating on convection inside a duct and some problem on mass transfer. Okay. So, with this I will be ending up this course. Okay. Every week you will be getting some assignments, okay, which you need to submit to us, and at the end of fourth week we will be having one examination. If you want to get certificate, you have to appear for the examination. Okay. So, let me go inside. So, before going to the topic, let me tell you what are the books you can follow if necessary. So, very good books are there called Burmester, L.C. Burmester. The title of the book is Convective Heat Transfer, published by Wiley InterScience publisher. We are having some more books. This is also very good book by Arpasi and Larsen, okay, V.S. Arpasi and P.S. Larsen. The title of the book is once again Convective Heat Transfer. This is available with Prentice and Hall, okay, Prentice Hall publisher. Then this book is also very good by Bejan, Adrian Bejan, Convective Heat Transfer. Publisher is Wiley and Sons, okay. Even you can refer Case and Crawford, W.M. Case and M.E. Crawford. Once again the title is Convective Heat Transfer, and this is available with McGraw-Hill, okay, McGraw-Hill publisher. So, all these books are very nice. If you want, you can suggest these books also along with this course, okay. Let me go to the outline what we are going to discuss in this lecture. We will learn about basics and applications of heat transfer. As we are beginning the course, so we have to learn the very preliminary basics and applications. Then we will be going for classification of heat transfer and know different modes, okay, as well as we will discuss about the governing laws, okay. Then we will be seeing what are the different types of convective heat transfer available and its occurrence over flat plate and circular duct, okay, because first 9 lectures we will be having this flat plate and then rest lectures we will be having on circular duct. So, these two cases we need to understand in this lecture, and then finally I will be giving you different non-dimensional numbers which will be important for convective heat transfer. I will be also telling you the physical significance of those numbers, right. So, let us go inside. So, first let me tell you what is heat. Heat is nothing but it is actually a form of energy which can be transferred from one system to another system, okay. So, this is actually energy, nothing but energy, okay. Now, the science which deals with the determination of rates of such energy transfer is called actually heat transfer, okay. So, if you are having energy transfer, to cater that one, to know the energy transfer, we are having a subject called heat transfer. Here I have shown two extents of heat. So, here you can see very hot objects, fire or a cup of tea, you can see the vapor coming out, and in the other side you can see the ice, okay, having certain less than 0 degree centigrade temperature, okay. So, we are having some spontaneous rule for transfer of heat from one side to another side. So, the rule is always heat transfer spontaneously from high to low repository, where we are having high heat repository to low heat repository, heat will be transferring spontaneously. Then repository is actually characterized word called temperature, which is coming in thermodynamics, so you have learnt already. Then high temperature repository is called source and low temperature repository is called actually sink. So, these are spontaneous rule what heat transfer follows. Now, there are exceptions also. So, if you are having exceptions, those we call different heat transfer devices. So, in those devices we have to obey second law of thermodynamics. So, in your thermodynamics knowledge, you know what is second law of thermodynamics, and you have already learned that how heat transfer can be regulated using second law of thermodynamics. Here I have shown some molecular structure of vapor and liquid. Over here you can see these molecules are very much compact, but here molecules are flying away. So, here you can have higher temperature, okay, to have these agitations, and here we are having lower temperature to have the compactness, okay. So, temperature difference or convection actually determines whatever phases will be there. So, in this subject we will be also discussing about phase change. So, this will be important. Till now whatever we have shown over here, these are related to single phase things only, okay. So, phase change can also come with convection, right. Next, let me show you some utility. There are multiple utilities, but here I have named a few to save my time. So, first utility what I am saying is solar water heater. So, you have seen, let us say this is the roof of a house. At the roof you can have this type of solar collector, and from there solar ray whenever it comes over here. So, it actually comes in this in the copper tubing carrying hot water, and this is the manifold which actually gathers all the water, and then it can supply hot water for different purposes. For example, hot water tap can be there, there can be hot water heat exchanger through which the room will become hot, and finally this pump can once again give back the cold water after heat transfer, give back the cold water to the solar chamber once again. So, here you see the whole phenomenon is driven by heat transfer. Here also heat is being transferred, here also inside the room heat is being transferred, and once again whenever it has gone back, it is once again ready for new heat transfer stages, okay. So, solar water heater is a perfect example for heat transfer utility. Next, a tube, a 2 tube pass, 1 cell pass, cell and tube heat exchanger. So, heat exchangers are devices where exchange of heat from one phase to another phase we deal. So, there obviously heat transfer will be important. Some devices we call condenser, evaporator, these are there in air conditioning refrigeration units. Even you can find out condenser in power plants. In power plant we can also have feed water heater and steam generators or boilers. So, all these are actually heat transfer utility, okay. So, here I have shown a schematic of shell and tube heat exchanger. So, you can see all these tubes, and we are having flow of another fluid via this inlet and exit over here to have some sort of heat exchange between the fluids, okay. Next, another one I can say is this this figure. You can see this is nothing but a blast furnace, okay, where air is blowing into the furnace to maintain temperature that is higher than 800 degrees centigrade, okay. So, it is actually required for melting iron, okay. So, here you can see iron is being melted and it is flowing into the ladle, okay. So, it is flowing into the ladle for casting somewhere else, okay. So, this blast furnace is perfect example of heat transfer utility. Now, as we have talked about this ladle which is being carried out, and that will be used for actually casting later on. So, casting is nothing but giving form of your desired shape, okay. In manufacturing it will be very important. So, this is actually example of a continuous casting machine. So, continuous casting can be achieved by cooling the molten metal, whatever you have melted over here, that you cool and give some desired shape, okay, in a conveyor system, okay. So, precise temperature control is critical for the quality of the final product. So, here also heat transfer takes a major role, okay. Apart from this, in our earth we can have weather study. So, you see all of you are aware that during daytime the sea breeze comes, okay, towards the land, okay. So, sea breeze whatever you are having, that comes towards the land, and as a result and this is actually result of natural convection, okay. So, this happens due to natural convection, and at night time the wind blows from the land to sea, okay. So, this just reverses from the land to sea, it actually blows, okay, that is also due to natural convection. So, here also you can see our weather changes by virtue of the heat transfer. So, this is also a perfect example of heat transfer utility. Apart from this, there are various other examples. I am not mentioning all. Even our human body is having heat transfer utility. Air conditioning system, definitely heating systems whatever we use in cold countries, electronic component cooling. So, all these laptops and PCs and cameras, smartphones, all are having this heat transfer equipments over like this. We are having power generation, so power plants, and refrigerator systems definitely is having concept of heat transfer, okay. Apart from this, there are many more. So, it is very interesting subject to learn heat transfer. So, first let me show you that what are the different modes of heat transfer. Basically, we are having three different modes. Modes are conduction, convection and radiation, okay. First, I have given small example of heat transfer. Let us say this is fire of heat or heat source. If you try to take the heat via a iron rod, okay, and you touch the rod over here, then you can see that this side of the rod is very having a very high temperature and it is very low temperature. Through the solid the heat will transfer, which is nothing but actually conduction. And if the heat is being transferred via air, okay, so there is predominant motion of the medium, okay, to transfer the heat from the high temperature to low temperature side. So, that is convection. On the other hand, if heat come a significant amount of distance without disturbing the medium, that is actually called radiation. For radiation, medium will not be involved, okay. So, this heat can be observed from a very high distance, but here for convection you have to keep a certain distance, so that heat can be taken from high temperature to low temperature. To explain this one, I have given a small story over here, that let us say here we are having a house which is burning, okay. So, it is burning, so we have to extinguish the fire. So, here we are having some water well, let us say, okay. So, in this well we are having water. So, my task is to throw the water or take the water to extinguish the fire in the house, okay. So, you can call that this is actually high temperature source, this is low temperature source. So, we need a transfer of water or heat, okay, analogous to heat from high temperature to low temperature. Now, let us see different modes over here. So, what the inmates of this house can do, they can take a bucket. First they can take a bucket and then with the bucket they can pick up water from the well and they can run, okay, like this person how he is doing, he can run and then go to the house and then throw the water to extinguish the fire. So, this is the first mode where the person is running, okay, the distance between the wall and the house, okay. And then here another way is that, let us say all the inmates, they form a human chain like this, okay, starting from the well to the house, and the bucket is being filled up by the nearest person to the well, and he is, after filling the bucket, he is actually transferring to the next person is transferring to the next person. Like this, the bucket is reaching through the human chain to the person nearest to the house, and he is actually responsible for throwing the water to the house. So here you can see the persons are not moving, the bucket is actually shifting from one person to another person, okay. So the predominant motion of the persons are not there, okay. And third one, you see, they have actually taken one hose, okay, let us say they are fire extinguisher company, they have taken a hose, and without movement, what they have done, they used some other mechanism, pumps or something like that, they have thrown the water to the house, okay, taking water from the well. So now if you consider these three cases of, you know, transfer of water from the well to house, you can find out this is having predominant motion, the person is actually doing some predominant motion. So this is actually comparable to your convection, which we are going to study in this course, okay. Here you can see only the persons are taking the bucket and passing to the next person, which is analogous to your conduction. So there is no predominant motion of the medium, and here the medium is no longer required, okay, by virtue of some other mechanism which is pumping the water, they are actually trying to extinguish the fire. So this is analogous to your radiation, okay. So all three modes I have shown you using this example, okay. Next, as I have to tell definitely about conduction, convection and radiation. So conduction is excitation of medium without bulk movement, okay. So here you can see it is actually fire pot, over that you are having a kettle. So heat is being transferred from the fire pot to the kettle via solid, okay, without the bulk movement. So this is actually perfect example of conduction. Convection, bulk movement of medium will be necessary. This is actually via convection, this person is getting via convection, okay. So air is moving like this, and the cat is getting via convection. It cannot see the fire, but via the air it is getting the convection, okay. On the other hand, no medium is required for heat transfer via radiation. If they can see each other, no medium is required, the person can directly take the heat from the fire, okay. So these three modes once again can be explained from this small fire pot example. Apart from these three mediums of heat transfer, we are having phase change also. These are all single phase heat transfer modes. In phase change, we can have boiling condensation for gas liquid domain, melting solidification for liquid solid domain, and sublimation deposition for gas solid domain, okay. So convection, our interest is actually lying in this zone where gas and liquid is being involved, so boiling and condensation. Some convection you can also see in these two domains, but majority of the times the convections are in the lighter phase. So we will not be studying these things in detail, we will be concentrating on this one, okay. Next, let us go one by one in different modes. First mode is conduction. So in conduction, what happens, let us say we are having two planes, okay. So let us say this is one plane, and on the opposite side there is another plane having temperature TH and TC. Now as it is high temperature, this is low temperature, so spontaneously heat will transfer from high temperature side to low temperature side. So we can write down this Q, or heat transfer Q through this slab is actually proportional to TH minus TC. So which is nothing but actually your temperature change between the planes, TH minus TC. So if TH minus TC increases, then definitely heat transfer will be increasing. We have also found out that if this length of gap between the, if the gap between the plates decreases, then definitely heat transfer rate will be increasing. So L is actually inversely proportional to del Q by T, heat transfer rate, as well as if the area increases. So this is the surface area of the plates, okay, both the plates are having same surface area in this example. If this this A increases, then definitely we will be finding out heat transfer rate increases. So we get that del Q by del T, heat transfer with respect to time is proportional to A, proportional to Th minus Tc, and proportional to 1 by L, and we give the constant here over here as K. K we call as thermal conductivity. The unit of thermal conductivity is watt per meter Kelvin. Okay. So this famous law has been given by Fourier, so that is why we call this law as Fourier's law. Okay. Next, if we try to find out what is the thermal conductivity, so this is actually a property of material. Diamond is having very high thermal conductivity, whereas K is having very low thermal conductivity. So air can be used for different insulation purpose, okay, as well as we can have different woolen clothing which is having low thermal conductivities. Okay, for window glazing we can use air for having low thermal conductivity, and it can act as very good insulator. Some values of thermal conductivities I have mentioned in this table. You can see air is having very low 0.024 thermal conductivity, okay, whereas diamond is having very high 2450. Okay. So metals are actually good conductors, and electron transfer energy from hot to cold. Okay. So actually the in conduction the electrons actually becomes agitated and transfers from one molecule to another molecule. So this becomes important, electron transfer becomes important for conduction mode. Let us see the next version, which is very important for us, convection. So for this we will be understanding Newton's law of cooling. So Sir Isaac Newton has given this law. So what he is saying, that if you are having a hot let us say a block of temperature T1 and it is being open to a free steam air of temperature T2. So he said that there will be heat transfer from this hot block to the air, so the which is having temperature T2, and that heat transfer will be actually proportional to T1 minus T2, the temperature change between the block and the neighboring air. Okay. So and also he has said the area will be very important. If area increases, then heat transfer increases. So he said Q is proportional to A and Q is proportional to T1 minus T2. Okay. And if you give the constant, so that is that can be called as H, and now we call this constant as convective heat transfer coefficient. Okay. So we will be doing detailed discussion about convective heat transfer coefficient in this course. The unit of convective heat transfer heat transfer coefficient will be watt per meter square Kelvin, okay, or watt per meter square degree centigrade. Some example of convective heat transfer coefficient I have given over here. So quickly I will be introducing what is free convection, what is forced convection. So you can see for gases and for liquids convective heat transfer varies. Okay, free convection for gases is having very low convective heat transfer coefficient, whereas forced convection for liquids is having very high convective heat transfer coefficients. Okay, forced convection heat transfer coefficient definitely depend on the velocity of the fluid. Okay, so Reynolds number will be important. Okay. Now value of H actually depends on what is the geometry of the surface, what is the nature of the fluid, what is the property of the fluid, and what is the velocity definitely. Okay, as I have said, velocity is important. Next, let us see what are the different types of convections available. As I have said, these two words I have used, forced convection and free convection or natural convection. Okay, free or natural both are same. So here you see this is a hot egg, okay, which we want to cool down by airflow. So first case what we have done, we have used a small fan to blow air on the hot egg. So here you can see the air is having some predominant motion which actually is being generated by the fan. Okay, so this you can see motion is the cause over here which is causing the convection. So this is actually forced convection situation. On the other hand, if you just keep the hot water in normal air, then you can find out the air will be taking the heat of the egg and it will move up, and subsequently higher density air will be coming in contact with the hot egg. So this type of cells, convection cells will be generated always. This type of convection cells will be always generated which will be taking the heat, and this mode is actually called natural convection. Okay, here the motion of this air is actually the effect, okay, effect of heat transfer. Here the motion is actually causing the heat transfer. Okay, so this is basic difference between forced convection and natural convection. And in this course we will be also seeing internal flow and external flow. Internal flow is nothing but flow inside a duct. The duct can be a pipe, the duct can be a rectangle triangular pipe or something like that, some other cross section, and in external flow is whenever there is some flow over a open plate. So, let us say this is a plate fixed like this on the free stream, and here you have some velocity. Okay. From fluid mechanics, you know there will be one velocity boundary layer, and velocity profile will be like this only. Here also you can see in case of internal flow there will be a parabolic velocity profile. In case of energy, thermal energy, or in case of convection, we will be finding out we have temperature profile like this. We will be having detailed discussion of this one in due course of time, and here internal flow will be having the temperature profile like this, and finally the temperature profile will come like that. Okay. So, some terminologies are involved called thermal entrance length and so on with internal flow we will be discussing in this course. Okay. So, after introduction of this different types of convection, let us see what is radiation, the third mode. In case of radiation, actually this has been proposed by Stephen and Boltzmann. So, that is why it is called Stephen and Boltzmann law. They propose that emission heat transfer from a hot body is nothing but proportional to the surface area of the body, AS, and it is actually proportional to fourth power of the temperature of the body. Okay. So, he has proposed Q is proportional to A, they have proposed Q is proportional to A and Q is proportional to T to the power 4. So, once you give the constant that is called actually Stephen-Boltzmann constant, the value of sigma can be found out as 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. This is very important. Okay. So, usually we call black body. So, in case of black body, it is actually the idealized surface, okay, which emits radiation at the maximum. So, black body can emit radiation at the maximum. So, if we think about black body, there are some black bodies, sun is a perfect example of that one. So, it emits the maximum. Okay. Now, for the real surfaces which is not a black body, so we can find out some fraction of this maximum possible emission is actually being obtained. So, we give this coefficient epsilon, which is nothing but emissivity. The value of emissivity is 0, in between 0 and 1. If it is 1, then it becomes the black body. Okay. So, we get, if this is black body, then this becomes equals to 1, and this equation actually converts into this one. Okay. Here I have given some example. If the body is having 400 Kelvin temperature, so Q emission will come, if you put the value of sigma from here, the Q emission will come 1452 watt per meter square. Okay. So, here you see this Q dot, and this Q dot is actually per unit area. Okay. So, area I have considered 1 over here. Okay. Remember, here you need to put the temperature in Kelvin. Okay. Next, some emissivities, this emissivity which is in between 0 and 1, I have mentioned for different materials, starting from aluminum foil and white paper. White paper is having very good emissivity, okay, almost near to black body. Okay. So, this we can see like this. Black paint is also having very good emissivity. Then another factor is also there, which is called absorptivity. Just like emission, any material can absorb also emissions. So, the fraction of the radiation energy incidence on the surface that is absorbed by the surface. So, whatever is coming on the surface, how much fraction it is actually being absorbed by the surface is called the absorptivity. The value will be once again in between 0 and 1. Okay. A perfect black body actually absorbs everything. It emits highest and it absorbs everything. Okay. So, this is having the absorptivity equals to 1. Okay. And these two are actually absorptivity and emissivity, they are related by Kirchhoff's law. So, the Kirchhoff's law is the emissivity and the absorptivity of a surface at a given temperature and wavelengths are equal. So, alpha and epsilon they are equal. Okay. And here I have given you some idea that how emissions are being absorbed. Okay. So, you see Q incident came, alpha fraction, absorptivity fraction of that emission is actually being absorbed and rest has been reflected. So, 1 minus alpha into Q has been reflected. So, similarly there is another term called reflectivity. So, reflectivity is nothing but 1 minus alpha. Okay. So, after that let us see different non-dimensional numbers which we will be reading in this course in our convection course. First one is bio number, this is nothing but HL by K, ratio of internal thermal resistance of a solid to the boundary layer thermal resistance. Then capillary number Ca, mu V by sigma, ratio of viscous force to surface tension force. Eckart number Ec is nothing but V square by Cp into surface temperature minus free stream temperature. It is actually kinetic energy of the flow, this is flow, kinetic energy of the flow relative to the boundary layer enthalpy difference. Eötvös number EO is nothing but del rho into L square by sigma. So, this is actually gravitational force to surface tension force ratio. Fourier number FO is actually alpha T by L square. So, it is actually ratio of conduction heat rate to the rate of thermal energy storage. So, whatever energy it is being stored inside the solid, that is Fourier number. Next we are having Grage number. So, you see in Grage number, that is nothing but ratio of thermal capacity to convective heat transfer. So, m dot Cp by Kl. Grashof number will be important, GR, Grashof number will be important for natural convection. Gb delta T, Ts minus T infinity is the temperature gradient between the hot surface and the ambient into del L cube by nu square, okay, ratio between buoyancy and viscous force. Jacob number Cp into delta T by del Hfg. So, this is the latent heat, del H vapor. So, this is the latent heat, ratio of sensible to latent heat absorbed during liquid vapor phase change. So, this is important for phase change processes. Lewis number will be important for mass transfer. So, alpha by D, D is the mass diffusivity, ratio of thermal and mass diffusivity. Nusselt number will be important everywhere in convection, HL by K. So, this is dimensionless temperature gradient at the surface. Okay, this is having similarity with the bio number, but bio number is for solid, here Nusselt number is for the fluid. Then we are having Peclet number. Peclet number is VL by alpha, dimensionless independent heat transfer parameters. Okay. Then we are having Prandtl number. Prandtl number is nu by alpha, ratio of momentum and thermal diffusivity. Rayleigh number will be once again important for your natural convection. Grashof number into Prandtl number. So, this is once again used for natural convection. Reynolds number already you have seen in your fluid mechanics course. So, rho L V by mu. So, this is inertia and viscous force ratio. Smith number will be important, Smith number and Sherwood number, these are important for mass transfer. Nu by D is the Smith number, which is the ratio between momentum and mass diffusivities, and Sherwood number is nothing but HmL by D, mass transfer coefficient into L by D. This is dimensionless concentration gradient at the surface. Okay. So, with this I will be ending this lecture. Let me summarize this lecture what we have understood. So, we have studied fundamental difference between different modes of heat transfer. We discussed possible convection configurations and their applications. We have detailed discussion of different modes of heat transfer along with the governing laws, and we have learned different non-dimensional numbers in the context of convective heat transfer. Let me now try to test your understanding what you have learned in this lecture. So, first we are having 3 questions over here. First question is which of the following is not single phase mode of heat transfer? So, you have to figure out this 2 phase heat transfer over here or phase change heat transfer over here. So, conduction, convection, radiation and boiling. So, obviously you know the correct answer is boiling. Okay. Next, which law is not applicable for heat transfer? So, we are having Fourier's law, Newton's law of cooling, Newton's law of motion and Stefan-Boltzmann law. So, we know that Newton's law of motion is not related to heat transfer, this is related to mechanics. So, this is the correct answer. Which one is not the non-dimensional number? Hg, Ra, Gr and Pe. We know that Ra is Rayleigh number, Pe is Peclet number and Gr is Grashof number, but Hg is actually symbol of mercury. So, this is the correct answer, Hg. Okay. So, with this I will be ending this lecture. In our next lecture we will be discussing about balance of total energy. If you have any query related to this first lecture or any other generalized query about convection heat transfer, please keep on posting in our discussion forum. Thank you very much.